I will do my best to make this quick. So fundamental theorem calculus part 1. I want to consider a function f that's continuous over such an interval. And I want to define a whole new function g as such. Notice how the input of g is the upper bound of integration. I'm going to prove to you that the derivative of g is just f. This may be a very theoretical result, maybe not something you want to use on a daily practice or daily schedule, but we will use it here and there, particularly to develop some interesting results like the fundamental theorem part 2. So first things first, take a peek at this. That is nothing more than the area from A to X to a place H underneath the graph of that thing right there. And take a look at this. I think likewise that's nothing more than this. But now take a peek at what happens when I look at the difference of those two. I think this represents the area from here to here under the curve, but I'm going to take away the area underneath the curve from here to here. Is that not merely going to leave me with the area between here and here? And so I think with my limited board space, another name for that difference on the right-hand side is simply this definite interval. The area from here to here underneath the graph of this. Just think I'm going to manage this with my board space. Let's take a break. Take a peek at how, when it comes to this function right here, since I'm claiming that I've got continuity over some closed interval, then I do think this thing right here attains a maximum value and a minimum value. So take a peek then how this represents the area underneath the curve from X to X plus H. And that area should be bounded above by the rectangle I create, whose width may be X plus H minus X, but whose height is the largest value the f attains. So I'm assuming this is an upper bound for ft over that interval. Likewise, I have a lower bound, and so here's the area of that smaller rectangle that you saw earlier. Now, technically speaking, I'm being silly. What's inside the parentheses is just h. So if you now let me rewrite all this, but replacing this with this alternative name, then I think I now have the following. That this difference is bounded above and bounded below by these two beasts respectively. So allow me to dive in and massage that double inequality. So if you allow me to divide all three sections by h, I think this is what I get. I say I think this, like, I could be wrong. Technically speaking, if h is negative, the inequality is going in the reverse direction, but I promise you the same result carries out. And if I take the limit as h goes 0, then notice how in the middle, assuming I go to 0 from the right-hand side, technically speaking, then I have nothing more than the derivative for g. But take a peek at my pretty picture. If h goes to 0, then I guess the only y value I really have is f of x. And so f of x ends up being an upper bound and a lower bound for g prime of x. Meaning, of course, I have just proven what I want to show.